we can express this uncertainty as thinking about the probability of getting the data that we observe given the underlying process. Okay, so the underlying process is what really happens, is all the cases that are really in the population, all the cases of a disease, and the data is what's being observed, and there's some sort of probabilistic relationship between the two. Okay, now with our model, what we're trying to replicate is the underlying process. So a way of making this link between the data and the model is simply by saying, okay, there's a probability given some model output, so given our trajectory of the model from a set of parameters and initial conditions, of that giving us the data. So it's a probability of the data given model output. And I just want to, since I will use this notation quite a bit today, I'll just want to spend 3 slides for those of you who haven't had any statistical training or haven't seen probabilities for a while, just 3 quick slides on basic notions of probability. There's a nice quotation by Laplace from 200 years ago, which is saying that probability theory is nothing but common sense reduced to calculation. And in fact, I think this is a good way of thinking about this, and there's nothing magical about it, but it's actually that the concepts of probability are often quite intuitive, and we can relate them to the real world. And so I've tried to come up with some real world examples here. So we will write in this talk, we'll write P that capital, so there's a random, we have something that varies randomly called capital A, and we say the probability that it takes value small a, we call this, we write this as P that capital A equals small a. Okay, and we often abbreviate this, and we just write this as P of small a. So this is the probability that random variable capital A takes value small a. For example, if you take the random variable of the weather tomorrow, okay, and you say you have no idea what the weather tomorrow is, and it's just completely random, then if you assess that probability, so the probability that tomorrow it'll rain, you can write as probability that W for weather perhaps is rain, or simply P of rain. Okay, so probability of rain tomorrow, probably about 1, given a recent experience, although it hasn't rained yesterday, so perhaps it's a bit smaller. And then probabilities, as you may know, are normalized so that the sum of all probabilities is 1. So there has to be some weather, so probability of rain, sunshine, snow, I don't know what else it could be, they will all sum up to 1. Okay. Second notion is the one of joint probabilities. So that's the probability that two random variables contemporaneously take 2 values. Okay, so take the probability that, so you have capital A is to have 2 random variables now, A and B, same as before, and you write this with a comma. So that's the probability that to get small a from random variable A and small b from random variable B. Okay, so imagine there's a cricket match tomorrow, India versus England, and so we may have the joint probability that tomorrow it rains and India beats England in the cricket, and this is the probability that the two happen at the same time. Now, as you may well know, or as I have been informed, cricket is not often being played when it rains. So whilst the probability of rain might be quite high, and the probability that India beats England might be quite high, the probability that they both occur at the same time may be relatively low. Okay, and just like before, we had the probability summing to 1, and similarly, we can obtain a so-called marginal probability, or we can get the probability for that A happens by summing over all the possibilities of B. Okay, and then last notion is the one of conditional probability, and this is similar to joint probabilities, but with an important difference. So this is the probability of getting outcome small a from random variable capital A, given that the outcome of the other random variable was a certain thing. Okay, so probability that capital A is small a, given capital B equals small b, or probability of A given B. Okay, so for example, the probability that India beats England at the cricket, given that it rains. Okay, so perhaps imagine cricket was played in the rain, and England was doing much better at playing the rain because it rains all the time in England, and then perhaps this would be smaller than the probability of India winning. So you get the idea, hopefully, and you can write this as again probability in India winning given rain. And these are related to joint probabilities because P of A given B is simply P of A and B divided by P of B. Okay, and you can also link them up. So if you have 3 things that happen, you have the chain rule, and so probability that A, B, and C occur is the probability that A occurs given B and C times the probability that B occurs given C times the probability that C occurs. And you can flip them around, so you can also do them in another order. Okay, so much for a brief interlude to probabilities, and it's just because I will use this notation quite a lot. And the last, actually one more concept about probabilities that will be important is the one of probability distributions. So probability distribution is something that tells you about the probability of different events of a certain type that can occur. And as an example here, many of you will know this, the Poisson distribution, introduced or famously used to estimate how many people died of horse kicks in the Prussian army. And so in some years, there were quite a lot of people that were kicked by a horse and died, and in other years, there were fewer. And on average, there were 0.61 deaths from horse kicks per year. And then you can find that the actual distribution, so every year, the probability of getting 0, 1, 2, 3, 4, 5, 6 of such cases is given by what is called the Poisson distribution, so there are certain values for these probabilities. Okay? And we can do two things here. We can, first of all, we can say, okay, so 3 people have been kicked by a horse and died this year. How probable was that? How unlikely was that? Okay, so we can simply read this off here. So 3 would be something like 0.001 perhaps, or 0.02. In fact, in R, you've got familiar with R a bit now, so there's this function d Poisson, which gives the probability density that x equals 2 for a Poisson distribution, given that the underlying rate is 0.61. So that's not this value here, so this must be for another rate. Okay. And secondly, so this is evaluating what you observe, and then secondly, you can take a random sample. So you can say, give me a random number that follows that distribution, and that will be a different one every time, but it will, if you do that many times, it will follow that distribution here of probabilities. Okay, so it's important to be aware of this distinction between evaluating the probability distribution at a certain point and sampling from the same probability distribution. Sampling is give me a random number that follows that distribution if I do it many times, and the other one is tell me my one number that I have, how likely it has been. Okay, so all of this extends to continuous variables. So you can think about something like what's the temperature in Chennai tomorrow? Perhaps it's something like this, probably a bit higher, so average perhaps 30 or so, perhaps a Gaussian around it. And the same notions as before, you use the same things, just that the sum is replaced by an integral. Okay. And you do the same thing with evaluating. So you can evaluate a certain value, and you can sample from the distribution to get a random value. Okay. All of this may seem relatively simple, or hopefully it makes sense, but all of these are important concepts to use when you do model fitting and inference. Okay. So let's think about, let's go back to our earlier scenario of having an infectious disease, and let's say we have an SIR model of an outbreak, and these are our data. And say that we know that each case has a probability of 1/2 per day of being observed. And every case, and the probability of each of these cases to be observed is independent. Then one way of thinking about this is that for each day, you have a Poisson distribution with this rate for each case. So the overall rate will be that number times the number of cases that there are really in the population. So let's say we have our model, and our model, our SIR model produces an output of something like this. Then we can look at each day independently. So say on day 10, for example, here we observe 18 cases. Our model says there should be 31.1 cases, and we have this reporting probability of 0.5. So what we do is we take a Poisson distribution, which is with a rate of 0.5 times this, or something like 15.55, and we take that Poisson distribution, okay, which is this here, which has the mean here, and this is the whole distribution, and then we look at the data point. Okay, so the data point was 18, so that's that here, and that gives us the probability. So that's the probability of observing this data point, given that this is the underlying true process. And so we put that distribution, this one here, we basically put that over here, and we read off what is the probability. Okay, and in this case, something like 0.078. And we can do this for all the data points, and then we simply multiply these probabilities across, and we get the what is called the overall likelihood of the observed trajectory, or the probability. We said earlier that it makes sense to think of probability of the data given our model, and we now write this as given our model output. Well, our model output depends in a deterministic model only on the parameters theta. So we have this probability of observing the data given theta, which is this product across all the data points. Okay, and we can make this a log likelihood. So often we do this on the logarithmic scale, because these numbers can be quite small. So we use the logarithms, and then the product simply turns into a sum of the logarithm of the individual likelihoods at each data point. And this gives us, so now this likelihood, as we have just defined it, gives us a connection between the trajectory in our model and the data. So you have this P of data given initial conditions and the parameter. Okay, and similarly to before, so now there's the idea that potentially we could sample from this, or we could evaluate. So this is, well, actually, I will come back to this, because the notion that I've introduced now is the one of likelihood. So I said that it makes sense to write this probability of the data given the model output, and because in a deterministic model the model output depends only on theta, we can write probability of data given theta, theta being both of the parameters, and this is what's called the likelihood, as I just said. So we call it I just introduced the notion of the trajectory likelihood, so this is called the likelihood, and we use the log likelihood normally because it can span a wide range of orders of magnitude. And the likelihood is, importantly, a representation of the so-called frequentist interpretation of probability. And just to briefly introduce what we mean by this, so this is about what our probability means, what our likelihood means, and what we mean by probabilities. So if you do frequentist inference, your interpretation of your model is that there are true parameters somewhere out there in the world. So for your given disease outbreak, there's a true beta and a true gamma, and the data that you get out are noisy. So because the data are noisy, every time there's an outbreak, then you might get different data, but what you're trying to find in your model fitting is the values of these true parameters. Okay? So I try to estimate these parameters, and so it makes sense to think of something like a maximum likelihood. You try to find, you run your model, you find the parameters with the maximum likelihood, and they are the ones that come the closest to the true parameters. And your probabilities express somehow the outcome of these repeated experiments, because the data will be noisy every time. And if you do Bayesian inference, you kind of look at it from the opposite way. So you don't think of this as true parameters and repeated experiment. You think there's just one experiment, or there's just one data set, and that is the truth. Okay, so there's not true parameters, there's only true data. And in fact, what we mean by these probabilities is not what happens if you simulate many or if you have many outcomes from these real parameters. What you now think is that, or the way you now interpret the probabilities is that they express your trust or your belief that the data are generated by a certain parameter. Okay, so now, and then so that makes for an important distinction, because now this is encoded in something which is called the posterior, or the posterior distribution, which is the probability of parameter given the data. Okay, because the data are given, and the data are the truth, but there's uncertainty in my parameter, so it makes sense to think of the probability of a parameter given the data, and that encodes my belief in that being the right parameter for the data. Whereas before we said, okay, so the stuff that's given is the parameters, and it's the data that are noisy, and I just want to find the maximum here. Okay, and because this is now a probability of theta, importantly, we interpret this posterior distribution as a probability distribution of a random variable, which is the parameter. Okay? So it might seem a subtle distinction, but it's actually important for there are actually important consequences for what you do when you do inference. So here you do maximum likelihood, and in Bayesian inference, you want to know something about the posterior, and what you want to know about it is what I'll talk about in the coming slide when you do Bayesian inference. So for the rest of this session and also tomorrow, what we'll do is we'll do Bayesian inference, which many believe is a more natural way and think about the kind of work that we do when you have models out there and uncertainty in the parameters. But both Bayesian and frequentist are perfectly valid and viable ways of thinking about this. But OK, so let's do Bayesian inference. And so we said that in Bayesian inference, we want to calculate this probability of parameters given the data. And you saw earlier, you saw the rule of conditional probabilities. So if you have this P of data on the other side, you can simply flip them around. So you have P of data times P of theta given data is the same as P of data given theta times P of theta. So to calculate the posterior, we can write it like this. And now here we have in the enumerator we have quantities that we can interpret very well. So there's this one here we've seen before. This is the likelihood. So this is the probability of getting the data from your model parameters theta. Okay? This one here we call the prior. And the prior encapsulate something that it doesn't depend on the data, and it just contains the parameter, and encapsulate everything we know about the parameter a priori before we even look at the data. And I'll get back to how you do that. And then you have this probability of data. So this is usually we're not so worried about calculating that, and we think of this simply as a normalization constant. So that we can simply say the posterior is proportional to some normalized version of the likelihood times the prior. Okay, so let's talk about the prior a bit. So I said that this P of theta somehow quantifies everything we know about a parameter before we even look at the data. And so, for example, let's say we look at a measles. We want to study a measles outbreak. Then we have some rough idea of what the value of R0 will be, because many measles outbreaks have been observed before in the world. Here's a distribution of R0 values with confidence intervals from different outbreaks. So we know that somehow, okay, our R0 for measles will probably be somewhere between 8 and possibly something as high as 42. And you can combine these together to form some distribution of probabilities. And so you take these from previous measurements, the literature, from expert opinion, and so on and so forth. So let's say I want to estimate R0 for my measles outbreak, and this is the likelihood that I have. So this is R0, and this is my distribution of the likelihood. But then from looking at the graph I showed you before, I know that the R0 for measles should be somewhere between 5 and roughly 25, and then very rarely a bit higher. And we said to get the posterior, you simply multiply the two together. So if you multiply those two together, you get perhaps something like this. So it's different from the likelihood, and it's different from the prior. It combines the two together into a distribution that encapsulate both what I believed a priori about my parameters and what I've learned from the data. Okay, now we said that the parameters are interpreted to be a random variable that's distributed according to the posterior. So we said this is this, probability of theta given the data, which is proportional to the likelihood times the prior. And now, so this gives me the probability of my parameters. I can't just look at one parameter, one value of the parameters, my best value of the parameters, and simulate that to, for example, make a prediction, because my interpretation here is of this posterior to be a probability that encapsulates how much I believe that this is the right parameter. I now, in trying to estimate some quantities, some derived quantities, or making predictions about the future, I now have to consider all of them and integrate over all of them. So if I want to calculate the expected value of any quantity given my data, I have to do an integral over the whole posterior times my quantity of interest. This should be an A. Okay, so for example, let's say we have an SIR model. In the SIR model, we have two parameters, beta and gamma. Okay, so my theta in the SIR model is beta and gamma. And I run my model, and I want to know what is my expectation for the value of R0. So if someone asks me what's the R0 value for this data, what would I give him as an answer? Well, so what I then have to do is I need to integrate over the whole posterior, and I integrate this R0, and that gives me an expectation value for R0. And similarly, if I have an SIR model and I'm in the middle of an outbreak and someone asks me what's going to happen in the next week, what I do is I estimate the posterior from the data that I have, and then I integrate over all the parameter values with their posterior probability densities to get trajectories for future spread. And I can associate probabilities with these trajectories, or I can give a best value of an expected trajectory. Okay, so how do we do this in practice? How can we start from a model and some data and then calculate something like an expectation value of R0 or do all of that stuff with the integral? Well, normally, so we can't really write, usually with something, even with something as simple as the SIR model, we can't write down an analytical expression of what that probability is. Okay, because of the SIR model and all the nonlinearities that are in there. Even though I can simulate my SIR model for every value of beta of gamma, if you give me some data, I can't give you an equation that tells you what that probability is of a certain beta and a certain gamma. So I have to do something else. And in fact, what we do is what is called the Monte Carlo approximation. And what we do in that is we replace this integral with a sum, with a discrete sum over a finite value of, in our case, parameter values. So a way to think about this, I mean, one classic example that's often cited is something like if you want to know what's the average height of people in Chennai, for example. Okay, so if you want to know what's the average height of people in Chennai, the right thing or the correct thing to do if you want to know the exact answer is to go and see every single person in Chennai and measure their height, and then you calculate the average. There's a much simpler way of doing it, which often gives you a very good approximation, which is you just walk up to 100 random people, and you ask them for or you measure their height, and you take the average of that, and often you get a reasonable approximation. Okay, that's exactly what you do in Monte Carlo approximation. Rather than doing something where you need to know the value of, say, this, or here more generally some p of x, but if you want to, where you need to know the value of this for every value of beta of gamma, you take some random values of beta and gamma, and you take the average over that. Okay, and then another way of doing that is if your samples come from this distribution, then you can simply sample over the values of your function that you want to get the expectation from, and you divide by the number of samples that you've taken. Okay, and so that's what we do in Monte Carlo sampling. And the reason you do this is if you think about the SIR model and some data and looking at some random values of beta and gamma, it's that very quickly in these kind of problems, you say if you have more than, or even if with two parameters, it's very difficult to know how densely you need to sample, how many values of beta and gamma you need to look at, and the behavior of the system can vary quite drastically just by changing the beta and gamma a bit. And you don't want to end up taking a lot of values for beta and gamma that don't really, that have your simulations not really come close to the data. You really want to make sure that you you don't waste a lot of simulation time with parameter values that don't give good fits to the data. And so that's what you do in Monte Carlo sampling when you try to generate samples that come from the posterior distribution, and then you average over that. Okay, so how does that work? What we want to do is we have some probability distribution, and we want to generate samples from it. Okay, so think of this as a general problem. Before we come to the posterior, think about you have some probability distribution. For every value of theta, you can calculate what that probability is. Okay, but you don't have a formula that describes you that distribution. And you can think of this as something like the posterior distribution in the SIR model. For every value of beta and gamma, you can run your model, and then you can calculate the likelihood. And if you know the prior, you can calculate the posterior distribution. So you can do this for every value of theta. But exactly as I said before, if you have 2 parameters, or think about even you have 5 or 10 parameters, which points do you sample? Where do you look? Where do you go? So instead, we do this Monte Carlo approximation where you draw random samples that have this distribution, and then you can average over that. And that makes sure that you take a lot of samples from areas where your posterior is high and you're close to the data. OK, but first of all, think of the general problem where you can evaluate this function at every value of theta, and you want to now generate samples from this distribution. OK, so how do you do this? Well, a simple way of doing it is called rejection sampling. And in rejection sampling, what we do is we take a distribution which we can easily generate samples from. So for example, we take this one here, which is simply a rectangle, and we take samples from that. And so first step is we find this distribution that we can easily sample from. So this is just a uniform distribution, and we can easily generate random uniform numbers. Okay, so these will be our samples from this here, from the so-called proposal distribution. And the algorithm then works like this. So you sample from this distribution. You draw a random. You take a random point from within that distribution, and then you look at. So you do 2 things. You take a random number. Okay, so you have your encompassing distribution. You sample. You take a uniform sample here, and then you also evaluate your function that you want to sample from at the same point. Okay, so you choose a random theta, choose a random parameter. You also sample a random value that is within your from your proposal distribution, and you evaluate your function at the same point. Now, if your value of the function is greater than your sampled random value, you as it's called, accept, and if it's smaller, then you reject. Okay, and then you just repeat that many times. So if you try to do that, so let's say you start from here, you draw a random number from here. Okay, you end up here. You evaluate your function at the point. Okay, and here the random value is smaller, so you accept. Okay, so I draw a little dot here for accept. Okay, now let's take another one. Take a random value here. Take a random value of the parameters. Take a random number between 0 and whatever here your maximum is. Take a uniform random variable here. Okay, again, you're smaller, you accept. Okay, and you keep going like this. So here's one. Okay, so here you draw a random number, and you evaluate your function, but here the random number is greater, so you reject. Okay, and you do this many times, and if you do this many times, you end up with samples of theta. Okay, you end up with values for theta, or with parameter values of your SIR model, if that's what you're doing, that are distributed according to the distribution that you want to sample from. Okay, and that was what we wanted to do. We wanted to generate samples of the parameter that follow the posterior distribution, while we can calculate what the value of the posterior distribution is at every value of the parameter, but we don't know in advance how we can generate samples from this. And this is a method to generate samples from this distribution. And what we can do now, so now we have all these samples of our parameters. So now we can do things like calculate the expectation value of R0, or create a number of future trajectories from each of these parameter values, and then from that have some range of expectations of how our outbreak will continue, say, if we're in the middle of an outbreak. Okay. So the problem with the rejection sampler is so it's not always easy to find that distribution. So you need to know what your maximal value of your posterior distribution is, and you don't always know this in advance. And also, you might end up rejecting quite a lot, especially imagine if this is so this was a one-dimensional example. If you imagine this was in 2 dimensions or even more dimensions, and you have a distribution which has a sharp peak, then you end up actually wasting a lot of samples because you reject. Okay, so this is the same problem as I said earlier. You might take a lot of samples, that are far away from the maximum of the distribution, and they don't contribute much to your expectation. And so you may end up rejecting a lot of samples, and you need to take a lot of samples or run many simulations in the concrete example of an infectious disease model in order to get enough samples to then make some meaningful statements. So another method, which is a bit, which tries to come around that problem by learning from what you have already seen, is what's called Markov chain Monte Carlo. And the difference here is that you don't just take random samples of theta anymore as before, but now you take samples that depend on what you have already learned about the system. And by that, you ensure that you end up simulating more from parameter values that are close to the data and that yield a high value of the posterior. Okay, so how does that work? So instead of defining a single proposal density, we build up a chain of samples. Okay, so we still have some kind of proposal every time, and we still take a random number every time. It's still a Monte Carlo method. So think Monte Carlo gambling. So it's a random. There's a lot of randomness involved. But now the random steps always depend on the previous step. It's like a random walk, rather than independent IID random samples. And the commonly used MCMC algorithm, MCMC standing for Markov chain Monte Carlo, is Metropolis Hastings. And our proposal density is now called not just Q of theta as before, but or Q of theta star as before. It's now Q of theta star given theta. So depending on where I've taken my last sample from, I propose a new sample, and somehow where I go will depend on where I've last been. Okay, and I'll show you the algorithm in a second, but the important thing is that it generates so-called unbiased samples. So even though you now generate this chain, and so you have some you get some correlated samples, you can relatively easily show in theory that this yields samples from the distribution which are unbiased, which are an unbiased representation of the underlying distribution. Okay, so let's see how this method works. So you start in the same way as before. So you start with some random value of your parameter theta. So again, here's a one-dimensional toy example. So you initialize your parameter value at some random value, or perhaps if you know something about the system, you might want to initialize it perhaps close to where you think there's a maximum of the posterior, but in general, you start it somewhere random. And then you take a random sample from your proposal distribution, which depends on where you've previously been. Okay, and so here it's just called Q of theta star theta. In reality, it's often a lot of work has to go into choosing a good distribution for this, for generating this random number from your previous sample. But think of this as something like, it could just be a random walk with drawing from a normal distribution or something, with a step size drawing from a normal distribution. Okay, so most times you're quite close, but sometimes you make a bigger jump. Okay, so you take this random number, and then you compute what's called the acceptance probability, which is basically the value of your function that you want to sample from at the proposed value of theta divided by the value of the function at the previous value of theta. And so it's if that is greater than 1, so if the new value is better or is greater than the one before, then this is 1, and this will be the acceptance probability. So this means you definitely accept. And if it's smaller, so if you end up somewhere that has a smaller value of the posterior, then sometimes you accept and sometimes you don't, and whether you do it or not depends on the ratio of the two. Depends on how much lower you've gone, basically. Okay. So in other words, if you start from, so we started from here. If you go there, if you go up, you always accept. And if you go down, you sometimes accept. You reject or accept depending on how far down you've gone. If you've gone down a half, you will still accept with a probability of 50%. So it's not a maximization algorithm. We're not doing some sort of hill climbing or anything like this, but we are actually sometimes going down. And by doing that, we ensure that we get unbiased samples from this distribution. So we get unbiased, our values of theta, our accepted values of theta will eventually be unbiased samples from this distribution. Okay? Now, importantly, we said this only works if the proposal distribution is symmetric, like a normal distribution, for example. If the distribution is asymmetric, I also have to include something that corrects for the fact that I'm perhaps more likely to go in one direction than the other. And this is to carefully maintain what is called detailed balance, which makes sure I get the unbiased samples. But forgetting about that detail, let's look at how that works in practice. So we initialize somewhere, we take a sample, and we compute the acceptance probability, which we said is 1 if you've gone up, and is some value between 0 and 1 if you go down. Okay? So in this case, so we go from here to here, so we go up. So in fact, we don't need to draw a random number. What you normally do is you get this probability, and then you draw a uniform number between 0 and 1, and then if that random number is smaller than the probability, you accept. If it's greater, you reject, and you stay where you are. You get a repeated sample from the one you had previously. Okay? And then you repeat this, and you end up with an unbiased sample from your posterior distribution. So you are somewhere, you propose. If the proposal is higher, you accept. If the proposal is lower, you might accept or reject. Then you're at your new place. You make a new proposal. If it goes random proposal, if it goes down, perhaps you stay where you are, and then you get another sample at that point, or you go depending on the value of that function at each point. Okay, and importantly, so as I said, what this means is that if you're near the mode of the distribution, you will tend to propose from there, and you will tend to have a lot of simulations from around there. In fact, you can tune your proposal distribution, and I said a lot of work goes into tuning your proposal distribution to be the right thing. You can tune your proposal distribution such that you get an acceptance rate in the end, or a frequency at which you accept, which is optimized in the sense that you learn a maximal amount of information from your system from the simulations you put into. So you don't waste any simulations. And in fact, there's some theory as to what the acceptance rate should be so that you maximize the amount of information gained given how much effort you put into, how many times you need to sample, or how many times you propose, or you need to simulate your model. Okay, now just to briefly talk about this proposal distribution. So the problem is, so here I've just sampled from a proposal distribution I've pretended I don't know how to draw samples from a normal distribution, and so I have a normal distribution with a standard deviation of 1. So it should be vaguely between 0 and 1 and somewhere here. And I start off at a random value, and then I do this Metropolis Hastings as I just described. And the problem is, in this case, I use a proposal distribution which has a relatively narrow variance. So it tends to propose quite close to where you are at the moment, or where you have last been. And then what can happen is that you do this random walk, but because you don't make very big steps, you tend to accept very often, and so you just do a random walk. And in fact, you don't learn much about your system if you accept all the time. Then you just know that you're sampling somewhere around the mode, but you're not actually generating informative samples from your distribution. And here, for example, after 5,000 samples, I've hardly crouched into the region smaller than 0, whereas my samples should come from something which also has some values between -1 and 0. Okay, so there's a problem with the proposal distribution if my jumps that I make are too small. If, on the other hand, my jumps are too big, what happens is that my Monte Carlo sampler gets stuck, as we say. So we stay in one place. So here we have, so this is here. I mean, one tick here is 1,000 proposals. So here for about 300-400 steps or so, I'm not moving. So here there are proposals being made, and they're never accepted. So here I reject too often. Okay, and because I reject too often, so I get some samples here, but I actually, again, this doesn't necessarily look like a normal distribution, and I get I get too often I get stuck in certain places, and so this yields a suboptimal proposal distribution, sample distribution here after 5,000 steps. Okay, so there's a problem if I make steps that are too big, because I tend to jump outside of, I tend to go too far. Too often I tend to go down, and I never accept. And there are problems if my jumps are too small. And in an ideal case, you explore the full shape of the target distribution. You don't get stuck, but you also don't just make small random walks. And then you get something which is more like the here what you would expect from a normal distribution with a standard deviation of 1. And what you aim for, so the optimal acceptance rate is 23.4%, but what you aim for is something between usually 20 and 40%. And for this, so what we usually say is that we aim for the trace, and so just looking at where my sampler is over time per iteration, look at my trace to look like a hairy caterpillar. This is generally the image we use. So if your trace looks like a hairy caterpillar, then you've done something right. Okay. So to summarize, so we said that we have this likelihood as probability of the data given a value of theta in the model, which expresses how close my model gets to the data. Okay, this is called the likelihood. And we said that in frequentist inference, all we're interested in is maximizing this likelihood. But that's not what we're doing, so forget about what I said. Instead, we'll do Bayesian inference, where you consider the posterior distribution, which is essentially the likelihood times the prior. The prior encapsulate everything you know about your parameters before you even confront your model with the data, so perhaps stuff from the literature or from previous observations. And so you multiply that with your likelihood that you can get from the model, and you get the posterior distribution. In Bayesian inference, we interpret the posterior distribution as being a random the distribution of a random variable, where the random variable is are your parameter values. And so it makes sense to think about sampling from that random distribution. Okay? And if we want to estimate some quantities, or we want to project into the future, what we need to calculate integrals over all my parameter values and over the posterior distributions of that random distribution. Okay? And we said that we can approximate this integral with a sum if we do Monte Carlo sampling. And I showed you as last bit the Metropolis-Hastings Markov chain Monte Carlo as one way of doing it. And tomorrow in the practical session, we'll give you some R code to do this MCMC, and you can have a go at it yourself. Okay. So coming back to our picture, so we said we have these parameters, and we have a prior distribution here. So there's some distribution depending on the value of theta. And then on the other side, we have the likelihood, okay? And in both times, there's a notion of generating random samples, or we can evaluate values, and similarly here. And this is what you'll do tomorrow with the functions that we'll give you in the practical. That's it. So I think that's it for the day. And I should ask, does anyone have any questions? Yeah, what do you get from doing Bayesian inference as opposed to frequentist inference? Yeah. So, well, I mean, I wouldn't think of this as or I wouldn't want to make a valued statement in terms of saying we get more from one than from the other, because you can make perfectly valid statements from frequentist inference, and you can make perfectly valid inference. To me, in many cases, the Bayesian inference is a more natural way of thinking about it, of thinking of the data as being given and thinking about uncertainty of the parameter given the data. I find that a natural way of thinking about uncertainty in inference, and also the notion of a prior, of some kind of prior information about that you know something in advance about what your parameter will be. And if you're looking at a flu outbreak, you won't be looking at at infectious periods of years or something. You know it'll be in the order of a week or something, and you have you can. It's a very intuitive way of incorporating prior information, having the prior. However, and also this sort of having the distribution of the parameter, and then using what you know for every possible value of the parameter in, for example, calculating future expectations or something, rather than focusing on the maximum parameter. But having said that, I think everything that you can do in Bayesian inference and every statement that you could make from Bayesian inference, you could come to the same result making an equivalent frequentist statement. So to some degree it's down to semantics, but I mean, yeah, and also with maybe perhaps one practical advantage of using Bayesian inference is that you have the powerful tool that is MCMC, and that is a truly Bayesian method because you generate samples from a random distribution. Okay. Yeah.
You were mentioning that the uncertainty arises from observation. And then you mentioned the distributions that you consider that are governing the observation process. Can you elaborate a little bit more on what distributions are appropriate for that?
Yeah. So the appropriate distribution depends on what you think the observation process is, really. So if you think about, for example, your observation as being cases, and every case has an independent probability of being observed, then this would be a binomial distribution. If you and in fact the distribution you choose is part of your model, really. So perhaps you choose a structure for your SIR model, and then the distribution you have for the observation is also part of the model choice. But okay, so if every case has an independent probability of observation, that's a binomial distribution. If you think that it's not entirely independent and there might be some correlations in there or some over-dispersion, you would use a negative binomial distribution. If you think that it's governed by more something like a rate, where every case has a probability per time of being observed, and you can have over-reporting as well as under-reporting, you would perhaps use something like a Poisson distribution. So it depends really on what you think the process is and what your model is for the observations. Okay.
In MCMC, Metropolis Hastings algorithm, we have to consider a particular distribution or general random numbers it generates.
So in the Metropolis Hastings, so we want to generate samples from our posterior distribution.
Metropolis Hastings by method of Metropolis Hastings algorithm.
Yeah, with the aim that we're trying to achieve with the Metropolis Hastings is to generate samples from the posterior distribution.
Yes.
And to do this, we generate random numbers from another distribution, from a proposal distribution, which is a distribution we choose, and it can be something simple that we can generate random numbers from, like, for example, a Gaussian distribution, a normal distribution, or even a uniform distribution. But it's quite common to use a Gaussian distribution. And so we use the random numbers that we generate from that to generate random numbers that follow our posterior distribution, which we don't have so I mean, there are established methods. It's relatively straightforward to generate random numbers from a Gaussian distribution, and the challenge is to generate random numbers that follow our posterior distribution from confronting the SIR model to the data.
My question is, we have to consider a particular distribution for that, or just it is a like posterior distribution, it generally generates a random number?
So the posterior distribution will be different for every time you compare, you have data and a model. So the posterior distribution encapsulates how good your model is in describing the data and how good certain parameters are or how likely you are for certain parameters to be the parameters that have generated the data. So you have some data, you have observed an outbreak, and you don't know what were the parameters of the underlying process. The posterior distribution encapsulates, via the link of your model, how likely a given value of the parameter is to have generated that data. Okay, and so that's a distribution. You interpret that to be a distribution of a random variable, which are your parameters, and from that you sample using Metropolis Hastings, from that distribution. From this P of theta given data, which is the probability that that parameter theta, or those parameters, say in your SIR model, have generated the data. So if you go back at if you look back at the at where we started, so you could say, for example, here, if this is your model output for your value of theta, then perhaps intuitively you say, okay, so that's quite unlikely to have generated that time series, perhaps, depending on whatever your observation function is. But say if that is quite unlikely, then the value of the posterior distribution for that value of the parameter would be lower than perhaps in something that looks more like the data. So the theta value that's been used here to generate the curve is more likely to have been the parameters that have generated the data, and therefore you would have a higher value of the posterior. And you can calculate the posterior for every value of theta by evaluating the prior, which is something you decide on in advance, and by reading the literature or whatever, and running your model and evaluating the likelihood, which is assessing how close the two are. And so you can, for every value of theta, you can calculate that value, that number, which is an expression of how likely the data are to have generated, the values, the parameters are to have calculated the data. And what you do with MCMC, you generate samples of your parameters. So you generate values of beta and gamma, say in the SIR model, pairs of beta and gamma, and these pairs of beta and gamma, they are samples from the posterior distribution. So you'll get a lot of combinations of beta and gamma that generate trajectories that are quite close to the data, and every once in a while you'll also get something that is not so close to the data, but not as often. And in fact, how often you get them is exactly given by the value of the posterior at that value of the parameters. Okay. Any other questions? Okay. Well, if there's no more questions, then I think we're done for the day, and we'll see you tomorrow at 9:30 for the lab session where you can try and do this yourself.